Let's look at kinematics in 2 dimensions now. And let's assume again that gravity is the only force that's acting on this object. Let's say a mass m is launched at an angle theta with respect to the horizontal on level ground at a speed v naught. We have a number of questions we want to answer. What is the total flight time before it reaches the ground again? What is the maximal height that it reaches before it turns back around? What is the range of the projectile, meaning what is the horizontal position at which it hits the ground again? What angle of launch maximizes the range? And also, what is the trajectory equation? Not parametric x of t and y of t separately, but what is the shape of the actual trajectory, y of x? As before, because the acceleration is a constant, it is only negative g in the y direction, we can use our constant acceleration kinematics equations. I've only written the first 3 here. Those are the only ones that we'll be needing. But notice that, again, this only works because the acceleration happens to be a constant. Negative g j hat, if you want to call it that. I've also taken the liberty of drawing a little sketch of our trajectory. Now we do have 2 dimensions. I'll call the x coordinate x. The vertical coordinate will be y. And notice that I've chosen my launch point as being the origin. That's convenient for a lot of reasons. So we have a mass here at the origin that is being launched at an angle theta above the horizontal at a speed v naught. And I've also labeled this maximal height location, and capital R will indicate the range of the projectile. Okay, so let's answer the first question, the total flight time. As before, there are a couple different ways of answering this question. I'll use the symmetry argument again. Here's our first kinematics equation written in the y component. At this maximal height, notice that my velocity is not 0, but it is perfectly horizontal. There is no y component of the velocity at that point, which means Vy is 0 there. Vx is not 0, but Vy is. The initial y component of the velocity requires us to think about a little bit of a right triangle here. The y component, looking at this right triangle, will simply be the speed of the projectile, v naught, times the sine of this angle. Notice that the y component is the opposite side of this angle. If you remember SOHCAHTOA, S-O-H, opposite over hypotenuse equals the sine of theta. So the hypotenuse, v naught, times the sine of theta should be that y component. Similarly, we know that ay is a given constant, minus g, and then t is the time it takes to reach that maximal height. But again, we're not looking for the time to reach the max height, we're looking for the total flight time. By symmetry, that's going to be double this particular t. Which means that this time, the time to reach the max height, is actually half of the total flight time. So we need a capital T over 2 here. This is easy to solve. And we end up with a very similar formula to the one-dimensional kinematics condition on the total flight time. The only extra factor is this sine theta, because it is being projected at an angle. So that makes sense. Now let's go ahead and calculate the maximum height. Again, there are a couple different ways of doing this. Let's go ahead and use, how about this third equation again? Notice that at the max height, we do know that the velocity in the y direction is 0. And I also know how to figure out how the acceleration and the position are related. At that maximal height, we know that Vy is 0. We know that the initial y component of the velocity is v naught sine theta, again from our triangle considerations. We know that the acceleration is negative g. We know that the y coordinate at that point is capital H, and we launched it from the origin. Solving for h, we can see a very similar relation to the one that we got for the one-dimensional kinematics of projectile motion. The only difference being this extra sine squared theta piece, which again comes from the fact that our initial velocity vector is not oriented perfectly vertically. To find the range of the projectile, we are going to have to invoke both vertical and horizontal motion. Let's write down 2 copies of the second kinematics equation. In the first case, my final x-coordinate when it actually hits the ground is r, the range of the projectile, the thing that we're looking for. We're launching it from the origin, so the initial x position is 0. The initial x component of the velocity will be v naught cosine theta. Again, SOHCAHTOA looking for this horizontal piece. That's the adjacent side to this angle. Don't forget there is a t here. The x component of the acceleration is 0. Remember, the acceleration is only vertical here. There is no acceleration horizontally because there are no forces acting horizontally. Okay, this looks pretty good, except I don't know what this t is. Now, actually, if we go back to our part A condition, we do know what t is. It's the total flight time. We could indeed plug this in right there and be done, but in practice, it's generally good not to involve previous calculation in each of your calculations, just in case you made a mistake. So let's derive it from scratch by looking at the y condition. Notice that my final height is 0. That's the height when we reach the level ground once again at the range. And the initial height, of course, is launched from 0. My initial y velocity is still v naught sine theta. This is the same t as above, which is capital T, the total flight time, but let's leave it for now. And we still have a minus 1/2 g t, well, t squared. Notice again that we can go ahead and factor a t out of this equation. They don't have to use the quadratic formula for that. So either t is equal to 0, which does indeed give you y equals 0, but that's the launch condition, so we're not interested in that. Or this thing in factor in parentheses gives you 0. Notice that, of course, that is the same capital T that we got for the flight time initially. So now let's take this value and substitute it in for the t of our horizontal kinematics condition. Substituting that t in here and now combining things together gives us v naught squared over g times 2 sine theta cosine theta. Indeed, we could leave it in this form, but actually it's nice to simplify this because 2 sine theta cosine theta is the double angle identity for sine. And we have that the range is v naught squared over g times the sine of 2 theta. Now that we have our max height, our range, and the total flight time, we're ready to ask some additional questions about how this projectile is moving through space. Let's go ahead and look at which angle theta maximizes the range. So we have this range. It does depend on theta as a double angle here. And we want to know what angle theta would make this as big as possible. Now you could do this with calculus by taking the derivative of r with respect to theta and setting that to 0. That is the maximization technique. Or if we just know a little bit about our trigonometric functions, we can ask, when is sine of an angle as large as possible? Well, the largest value of sine is 1, and that occurs when its argument is equal to 90 degrees or pi over 2 radians. That means that the maximum range occurs when 2 theta is equal to 90 degrees or pi over 2 radians. But of course, that only occurs when theta is equal to 45 degrees. In other words, a 45-degree launch angle will give you the maximal possible range. This kind of makes sense intuitively. If I launch this at an angle of 0, well, the formula gives me sine of 0, which is 0. But also, conceptually, if you're on the ground and you launch it horizontally, you'll instantly go down into the ground. 0 range. Similarly, if I launch it at perfectly vertical, theta equals 90 degrees, well, the formula gives me 2 times 90, which is 180, and the sine of 180 is also 0. But conceptually, it makes sense. You're firing it straight up, it'll just come straight back down and not go horizontally at all, so the range would also be 0. Conceptually, it tracks that halfway in between those should give you the maximal range. Finally, we have the question of what is the actual trajectory? What is this shape? You may already know that this is a parabola, but for the longest time, especially in antiquity and the medieval period, we really didn't know what this shape was. It was thought that maybe these were straight lines, or maybe the arc of a circle. So let's actually calculate the trajectory outright and prove the Newtonian view that this is indeed a parabola. I'm going to go ahead and once again invoke our 2 copies of this second kinematics equation. As before, this is actually a parametric description of this trajectory. I want to eliminate the time dependence to get y directly as a function of x as opposed to both x and y being functions of time. To do that, I'll solve the top equation for t, since it's a linear equation for t, and substitute that in for the t's here and here. Okay, we notice that there's a little bit of simplification. For instance, these 2 v naughts cancel in this factor, in this fraction. And we also see that sine theta over cosine theta gives us tangent. For the second term, there's not as much simplification, but I could rewrite the cosine squared in the denominator as a secant squared, perhaps, and I'll factor out that x squared to make it look like a quadratic. Indeed, if we look at it this way, I could rewrite this as a linear term in x minus some quadratic term in x. And if we really wanted to, we could even factor one more time. And using our result for the range equation that we had earlier, although probably leaving that in terms of 2 sine theta cosine theta, we end up having this linear factor times another linear factor, and it's easy to see that x equals 0 is an intercept. Indeed, that's the launch point. And x equals r is the other intercept. Indeed, that's the place where it hits the ground. So this does check out as being a parabola that is inverted, hence the negative quadratic coefficient here, and having the intercepts we expect. So we've proven the age-old, although not super old, proof of Newton that a projectile under the influence of gravity alone does follow a parabolic arc, as long as the gravitational field is assumed to be uniform.